And let me give you a definition. We have two. One has to do with something what we call the closed region. You're going to say that a region, and I'm going to talk about the region in R2 in an X and Y plane, is called closed if it includes its boundary. Okay. A region in R2 is called open if it doesn't. Okay, it doesn't, I mean, does not include the boundaries. Right? For example, if we're talking about a circle, okay, this region is open and this region is closed. So it's similar to the notation we had for open and closed interval, but we no longer can talk about interval here because we have two independent variables x and y. The second definition has to do with bounded, and this is a little bit sticky here, but we're going to say that a region in R2 is called bounded. It's not really sticky. It's sometimes people question why do we need this distinction between closed and bounded. And we're going to say that the region is called bounded if it is completely contained in a disk. The implication is, so we're going to write i.e. a bounded region is finite. To give you an example, we can say that this region, I'll choose here a square, okay? This region is closed because you can see that I included the boundaries. But if I put a disk around it, and it can be even, the vertices may coincide with the disk, now it is bounded. Okay? So we can say that the square is closed and bounded. There is a little distinction here that we require. Why do we need it? Because a lot of times, if we cannot talk about the square, but we know that, let's say, we know something about the property of whatever function that is bound, is the bounding function, then we know that, for instance, the area of the square will be no greater than the area of the disk, just for an example. All right? So we need that. And so this was one definition. And now what I'll do, I'll present you with the extreme value theorem for two variables. You may recall it for single variable. So extreme value And the extreme value theorem is pretty simple. It tells you that if a function is continuous in some closed bounded region in R2, then there are points in that region where the function has an absolute minimum and an absolute maximum. Remember, the extreme value theorem in Calc 1 told you that if you have a continuous function from AB on the closed interval AB, then at one point you'll have an absolute minimum and another point you'll have an absolute maximum. Okay. So even if it's a horizontal line, then every point of this, or if it's a horizontal line segment, every point on the line segment is both absolute minimum and absolute maximum. But if you have a certain curve on a closed interval, then on the curve you'll find one point that is the absolute minimum and the other point will be absolute maximum, at least one of each. Well, that's applied also here. That's what the extreme value theorem tells you. So let's write it, that if f of xy is continuous, so we need this condition, continuous actually in some closed bounded set D in R2, okay, then there are points xy in D such that x1 y1 is the absolute maximum and x2 y2 is the absolute minimum. Of f of xy in D. Alright, let's translate that to some workable example. Okay. Actually, before that, let me give you the procedure here, similar to the procedure that we had in Calc 1. So what is the procedure? If you remember in Calc 1, and I said that earlier, first we need to find the critical points, but then we evaluate the function value for the critical points and the endpoints, and then we compare, and the highest value is the maximum, the lowest value is the absolute minimum. Same here. Part 1 is find all CP in D and determine the corresponding function values. Part 2, we need to find all extrema of the function and boundary. And that's the tricky part. And you'll see in the next section we use technique called Lagrange multiplier to simplify this particular task. And part 3, but for the time being, just a comment here, for part 2 we're going to use some technique from calculus 1 to solve that. In other words, we're going to set up an equation in one variable that we find its maximum minimum to find the extrema on the boundary. Okay, and then the largest and the smallest. Obtained in steps 1 and 2 constitute the absolute max and min respectively. All right, now we're good. Now we can go and do an example. We got the verbiage out of the way. So